Oh boy. Try to have some fun. Not going to happen, but we will try. Let's start back here and see if you remember the answers to these. Yes, how do you know that? Mhm. These slides here, these are very close to type. This is what your exam questions will look like. What about the next one? Which one of those is false? Just be happy because I did actually think about just for fun putting a question on there. Which one of these is the most correct? Those are so much fun. What do we think? Yep, that one's not true. Body center cubic is two. But the rest of them, hexagonal layering is ABA. So if you go back up, see your hexagonal layering right here. Now you're not going to have to calculate anything for like a hexagonal cell. That you don't get into the more difficult cells until like 400 or 500 level solid state chemistry. I don't think anyone in here is planning on doing their PhD in chemistry. No? Like there's no, and then there's the look you had on your face. Like there's no, but then I look and I can just hear you screaming in silence. Ah, hell no. So it's not that bad. Okay. For unit cells having the same edge length, the simple cubic structure would have smaller density than a body centered. That's true. Why is it true? We do not answer questions in here like politicians. It's true because it's true. No, when we don't do that. See your body centered? You see your simple cubic? Yeah, simple cubic has one atom, body centered has two. Two atoms is more dense than one. Atoms in a solid consisting of only one element would have six nearest neighbors if the crystal structure were a simple cubic. Do you remember talking about that? Uh-huh. So if we go, when we look here, do you see that octahedral field of your simple cubic? You see that atom right at the corner? Its closest neighbors are going to be there, there. So it has six. It has an octahedral field that it sits in. All right, on to some new stuff. Metallic bonding. So instead of orbitals, uh, fun stuff, I was able to make this on the computer. This is actually the molecular orbitals for a metal. It's like just a big bunch of goo. That's because in your metals, your electrons take the form of kind of like a gas or a fluid inside the metal. Your positive nuclei are going to be at the lattice points, but your electrons are just going to be kind of all over the place. This is why metals conduct electricity very well. Can someone explain to me why this leads to good electrical conduction? All you need for current to flow is a delta V. Yeah, so if I put a potential difference across this, the charges are going to separate and those electrons are just going to move to wherever they need to. Another way to understand conducting materials is by band theory. I don't know what some of my students did last semester. Hey, in this class, why did you this class? No, we to a concert. That is not a reason. Not a reason. I will only accept if it's a band like the Red Hot Chili Peppers. It has to be something cool. It can't be one of these little pop princesses that no, absolutely not. But so what do we mean by band theory here, though? Okay, so you see way over here where it says on the left where it says insulators? Or take, for example, an atom like your diode, Li2. So that would be like right here, position 2. Do you see how far apart those orbitals are spaced? So that spacing, the larger that spacing, the more energy it takes to cross it. So insulators are over there where there is a large, what we call band gap. It takes a lot of energy for the electrons to enter from valence to the conduction band. But as we move over, the bands start to get closer. We get semiconductors. And as we move even further, we get to this realm where the bands, there's not only they're not a band gap, but they cross into each other. Those are your metals in particular. Those are your conductors. So you see the electrons there, they can go from valence band to conduction band very, very easy. We don't need a lot of energy to do. And once you get to a conductor, what you get over here is pretty much a continuum of available quantum states, where they're able to just cross from one to the other. Another type of material we have are alloys. Very generally, alloys are substances that contain mixture developments with metallic properties. They don't always have to be metals. So if you look at steel, you get a mixture of iron and carbon. I know, like when people are trying to sell you stuff, they always say this is high carbon steel. Well, it's just the more carbon atoms you have in there, the more you can call it like a carbon steel, a high carbon steel. You basically get the iron really, really hot and you douse it with a carbon source, oil, something like that. Someday when you take more advanced chemistry, that mean will be really, really funny. Is this not the metalloid? No. Metalloids are a certain type of element that kind of share the properties of metals and nonmetals. They're a weird stair-step pattern right there in the periodic table. Nope. A metalloid is a type of element that an alloy is a mixture. So the first type of alloy is a substitutional alloy. You notice some of the atoms from the pure metal are taken away and replaced with another compound. Looking at the steel, why do you use alloys? Real details. So steel is much stronger than iron. Can you tell me what's happening when all those carbons get in there? Because you know, the iron by itself is going to have that metallic bonding, that kind of cloud of electrons that move freely. What starts happening here? Why does that make the iron stronger?
So that has like full bonds, so it makes like a.
Carbon is going to start adding, yeah, so carbon is going to start adding some directional covalent bonds to the structure, making it much, much stronger. Well, what are some other things you get from alloys? You know, it's these some of these from pop culture actually was kind of right what it was talking about. He saw the very first Iron Man movie. And he said his suit was, he was mad, he said it's not iron, it's a titanium gold alloy. Well, why would he alloy titanium and gold? Very, very strong. What's its weakness? No, it's not it. It's very, very strong, but if you hit titanium with a pink shell, what happens to it?
It's like. You know, shatters.
Shatters, literally. So what happens if you hit gold with something? Like, then that's malleable. That's too weak to give much help. If you alloy the two together, you get the strength of titanium and the flexibility. So alloys, you can actually design them start giving you the best properties of the different compounds. Now we have what's called an interstitial alloy. It's a fun vocabulary word that everyone's going to get sick of saying, but if you see it on an exam, this is how they're going to say it. So an interstitial alloy still has all the original metal atoms, but it has another compound in the interstices between the atoms. Yeah, they can't just say space between the atoms, they have to call it the interstices. The steel is an interstitial alloy. And although that means funny, gold's actually really good for electronics. It does conduct and you can get a lot of control out of the circuitry. There's just right now we still have an section that brings the bars and going into the brand. No, it's like you have the day of pirates and then countries come along like, what are you gonna do with the gold? We're gonna bury it. Oh, it's the same thing. This is all right. Network atomic solids. So here you see some of what you've already seen before, but you have diamond, silicon dioxide, silicon carbide, graphite. You see why those are called networks. You see in them, but you don't see in the metal. Yes, very good. Yeah, the directional covalent bonds. And the network solids can grow and grow and grow into a macro structure. The silicon dioxide, what does it grow into? Kind of. Not being able to really discern my inside thoughts from outside thoughts, silicon dioxide got me booked off Instagram one time. It can be crushed into a powder. It's quartz. Because there was someone on there going, these crystals will feel your quantum energy. I go, that is not how that works. And they said, you're being insensitive. It's not how it works. Like, what do you mean by field? What do you mean by quantum energies? Are you saying that these discrete energy levels that are available have somehow been damaged? No, they're still available. Graphite. Where do you find graphite? Pencil lead. Be glad it's not actually lead. As much as I see some people chewing on pencils, we would have some real brain issues going on. Now, here's an example of why insulators are insulators. So this is the amorphous version of silicon dioxide, but you see those large band gaps, somewhere around 7 electron volts for the kind of an average for the silicon dioxide, and about an average of 6 electron volts for the diamond. Those large gaps are what really prevent these materials from becoming conductors. Now, technically, silicon dioxide can be considered a semiconductor. So here's a question: what's something you can do to a material, the semiconductor material, to take it from insulator to conductor? How do you bridge that band gap? Nope. It's not an enzyme. Huh? Yeah, you get it real hot. What about a quantum mechanical material? How would you do that? How would you cross the band gap for a quantum mechanical semiconductor? What if I told you it involved a particle? If I tell you it's one of the primary bosons, does that help? They're whole integer spin particles that they don't abide by the Pauli exclusion. So photons. Light will cause the electrons to jump the gap and start conducting. Bosons. Bosons, the force carriers in the universe. Without bosons, you wouldn't, it's like without the Higgs field, you would not feel gravity. The Higgs boson, it is the gravitational force carrier. So anything that has mass is subject to the Higgs field and then is subject to gravity. Believe it or not, all of you have your own gravitational fields. They're very, very tiny, but they're there. Wow, that is harsh. It's kind of like if you throw a baseball has a wave function. It's minute, but it's still there. It's just really difference in the size. It's the size, the scale you're working on. Now here, oh crap, I left it circled. Well, so here we have graphite. Look at that and tell me why graphite can become why graphite has conducting properties. What are they circling? Not waves. Those are band structures. So what you have there is you have conduction bands on the bottom, and they actually intersect. You have valence bands on the bottom, and they intersect with the conduction band. So that touching allows electrons to just cross right over. And if you're using slides to study, I know some people do. I'm also aware some people go, "What's studying?" But if you're looking at these, please just ignore the A, the gammas, the M's, K's. And so those are what are called symmetry points in a crystal. And you can actually calculate the band structure of a compound. It takes the mathematics where you have to take the structure of the crystal, flip it upside down into inverted space, and then you do path integrals from one symmetry element to the other, and then you turn it back into regular space, and what you get are these band structures. So again, if we go back up here, you see like in the silicon dioxide, you see that whole mess up there. Those are all conduction bands crossing into each other. So is silicon, if you can get the electrons up there, they have a lot of options for movement. Diamond, few less. Another thing that you notice with graphite that you should be able to understand that gives conducting properties. What are those rings? What kind of structure is that? Six-carbon ring. Not the six-carbon ring, but the donuts above and below.
Is that like a ABA structure?
Nope. Look at those. What kind of orbitals are those? Orbitals. What kind of structure do they form on the bottom? Pi structure. So that is a delocalized pi structure. The more delocalization you get, the more conductivity you can get. Now, here's a fun one. Okay, CO2. If all the stuff I didn't erase, can get done early. So based off what I have here, I want you to tell me why, someone try to tell me why CO2 forms a gas where silicon dioxide starts to form network structures. You think that PPV and that 3PV are going to interact with each other? You can build a form of pi structure? Because you see on the 3PV, you see the little bitty roads? That's your 2PV. We've forgotten molecular orbitals this fast. No, well, so think about it. So carbon dioxide is self-contained. It doesn't start forming the network of directional covalent bonds because it's very self-contained with its sigma and pi bond between the carbons and oxygen. Why does silicon dioxide not do that so well? Why do they want to form more of a network and more of these directional sigma bonds? Nope.
Electron, proton. Yeah.
They're still, it has to do with why there's safety in the early species. You see how carbon and oxygen both provide a 2p orbital for pi bonding? 2p orbital, we're going to have similar energy, the same symmetry. So they're going to interact much easier. It's much harder for a 2p to form a pi bond than 3p. Because I mean, look, you can see the symmetry differences just by looking at it. The 3p is also quite a bit higher in energy. They don't match symmetrically, they don't match energetically. It will happen, just not as much. So then you have those extra electrons in the silicon dioxide have to go somewhere. So then they start forming more, they start forming those network bonds. Yeah. Did anyone here have Timothy? Did he talk about, did you tell me, or did you talk about atoms in the same families? Why is something like carbon and silicon would form the same structure with oxygen? Why do they form that same molecule?
They're in the same, like column.
Yeah, which is what? They're not valence electrons, they're in the same column. What can we expect out of atoms in the same column? Same blue column. Almost, yeah, pretty much very, very similar chemistry. That's why they're grouped the way they are. Now, you want to talk about research that would have been awful. You had Dmitry Mendeleev. Apparently, Russia was so horrible that all he did was sit and construct the periodic table. Found out which atom behaved like other atoms, and makes you want to live in Russia, but you know. Do you imagine just going, life is so hard, I have nothing better to do. So it's that, and then I have students always ask me, why did Isaac Newton invent physics? Well, there was a period of time called the plague where he was stuck in his house, and it was the 1600s. What else was he going to do? In the 1600s, you either invented some kind of new realm of thought or you stare at a wall. All right, silicates. Silicates are all going to be based off these SiO4 tetrahedral groups. And they're going to chain together to make these nice little structures. Why does that kind of triangle represent tetrahedral group? Mm-hmm. What's a good molecule of the insect? Methane. Methane is probably your primary tetrahedral example. And so again, if you tilt it on its side like that, you can see that the three corners at the base, and then the one hydrogen that forms the top of the pyramid. Now, these silicon oxide networks are going to form anion. What's that? Negatively charged. So, see all those little openings in there? These are going to start to form crystal compounds where those openings are going to start to take on cations, which are positively charged ions. And please refer to them as cations. Every year I have someone look at the word and say cations, and then I leave the classroom and go and slam my head in the door. Well, I mean, it kind of looks that way, but no, it's cation. Like, what's a cation? Oh, all the things I can't say, I'll lose my job. Now, as you go along, these silicates are going to start to they're going to form a silicon to oxide ratio of 2 to 1, or oxide to silicon. So 2 oxides to 1 silicon, but they're in SiO4 units. Why does it become 2 to 1 and not 4 to 1? The network solid. Mm-hmm. So you see how all of the tetrahedrals, those tips are oxygens. And so you're going to go silicon to an oxygen to a silicon. And it just forms this network, which eventually forms a 2 to 1 ratio, oxygen to silicon. Here's a fun one, ceramics. Now, glass is not a ceramic. I use it as an example of a network solid. The 2 on there that are ceramics, feldspar and zeolite. Now, here you can start to see those silicate tetrahedrals. Now, in this case, it could also be an aluminum oxide. Well, the same kind of tetrahedral. And you can see the potassium being set up in those void spaces to balance out the charge. All of these ions coming together, their coulombic forces, their electrostatic forces are what's going to form the crystalline structure. Let's see. Glass is homogeneous and ceramics are heterogeneous. What does that mean? Kind of, yeah. So when you look at glass, do you see a single material or do you see pieces? It's very single material. That's how you know something's homogeneous. So like a solution that's homogeneous. I don't know, take like an acid solution, just it looks like water, don't drink it. But you can't see the different pieces. That's homogeneous. Heterogeneous, and so again, like you were saying, the glass is all silicon oxide. So that's another form of homogeneity. Heterogeneous, you can certainly see individual units. You can see the potassium ions sticking out. You can see all the different units. That is heterogeneous. Now for some real fun, semiconductors. Okay. So we talked about conductors, where there's no band gap. Talked about insulators. There's a ginormous band gap. Semiconductors have a band gap. So much smaller. So based on what you do to the semiconductor, they can either have insulator properties or conductor properties. Now, there's a couple of types of semiconductors we want to know. The first type is an N-type semiconductor. N-type semiconductor is when you take the semiconductor material and you dope in atoms that have more valence electrons than the atoms in the semiconductor. What did I just say? You have to last time to get all the jokes on. No, it's not. It's not what we mean. Here's what doping in chemistry means. Look at that structure there. Look at the phosphorus. What would be there if that was an undoped semiconductor? What would be where that phosphorus is now? See, it's silicon. So one of the silicon atoms was removed and replaced with phosphorus. That's what doping is. Yeah, so you're replacing atoms or units of the material with another atom or unit. So in this case, phosphorus has more valence electrons than silicon, so it brings those extra electrons with it. It becomes free or conducting electron. And so we're going to be talking about, have you ever heard in technology something called a particle hole pair? Yeah. Either we got a lot of catching up to do, or I am the world's biggest super nerd. Possibly both. Possibly both. Okay, so the extra electrons, this is what we call the particle. Okay, you have an excess of particle. Used for what? So N-type stands for extra negativity. Your P-type semiconductor, you're going to dope in an atom into your semiconductor material that has less valence electrons than the atom that was there. So again, down here at the bottom, you see the two dopants. You see how the phosphorus brought an extra electron. The boron came in electron deficient. And that left what's called a hole. Where there used to be an electron, there is now no electron. So P-type, of course, are positive type. The holes are going to be an overall positive charge. The way these work technologically is electrons will jump into the holes to fill the gap, and they say the holes move across the material. It's really just the electron jumps here, now you remove hole, electron jumps here, now you remove hole, so on and so forth. Which leads us to a very popular type of technology called a p-n junction. Can anyone explain to me where you guys, you definitely know what p-n junctions are. Where do you see them? Where do you think you use them? Think of electrons jumping into holes. When that happens, you get a release of energy. kind of. I don't understand biology. I don't know biology. But yeah, our biology students here, one day I was walking around the hall saying, I reject human, wish to return to monkey. And one guy goes, that's not how it works. I'm like, I'm a physicist, let me have this one. Oh, yeah. Kind of, because you get a buildup of a charge and then you release the charge on your unsuspecting sibling. So, you shock the shit out of it. So, what happens when an electron is at a higher energy and then settles into a lower energy? What does it mean? Photon. So a p-n junction is going to start to release tons and tons of photons. What is something you think you have that technology that's real popular right now that would do this in form really, really bright lights? It can be, the part of it fun, it's LEDs. What does LED stand for? Did you all think that you had lead in your TVs? No, it's a light emitting diode. So a light emitting diode is a really popular example of a p-n junction. And based off the type of material you have and how the electrons jump, that's what produces the different colors. So just like you think, you have the n-type that has all these extra electrons. You bring it together with the p-type, the electrons start jumping the gap and filling in the holes on the p-type, and you just get tons and tons of light. Now, I call it a diode. That's another reason you're so important. A diode is a very important type of technology because you can set them to reverse bias or forward bias. If you reverse bias a diode from your technology, it's going to resist a current flow. So diodes can be used as gateways, either allow current or disallow current based off the need of the system. Because sometimes you need to shut current down, you're going to melt the system. Sometimes you need current. The thing inside a computer, you know how you get either current or no current? What does that translate into inside a computer? You either have an open pathway or a closed pathway. Current, no current. What do those translate into? What? Well, kind of. So I only have two options. What do we call a system where there's only two specific options? You're getting there. What? I'm getting biology all the time. What do you call a species that's male and female only? Called binary. So inside of a computer, yeah, you get open, you get closed. If you have current, you get a 1. If you get no current, it's 0. That's what makes the binary code. And a lot of this is done with diodes. So your reverse bias is going to resist current. Your forward bias is going to excite current. And it's really because you see how you hook the battery up to the diode or the power source? All you have to do is change the delta V direction on the power source. And that's going to bias the diode in a different way. So again, in the reverse bias, see I put the positive on the right side, and that's going to cause all of the electrons in the inside material to go towards that positive and away from the junction. Same on the left side, where I put the negative sign there, all those positively charged holes, you're going to go towards that negative and away from the junction. So you're going to get very, very little particle hole pairing. Versus the other way, where I reverse the positive and negative, and so now all of the charges go straight for the junction. Now that you're super bored, let's try to answer some questions. Now, Remember, these questions are what your exams are gonna look like. Why we're practicing. This one, this first one is one that would probably make much harder than you have to. Simplest formula of a solid containing atoms A, B, and C in a lattice in which A occupies all the corners, B is in the body center position, and C is on all the faces. What do you think? Nope. How many atoms do I have? Remember, if they're on the face, how many of that atom do I have? So okay, so in a single unit cell, 3. Remember, in a single unit cell, face gets half an atom. So if you have a C on the faces, you'll get 3 of those. The body center is 1 atom, and corners is 1 atom. So it's an ABC for. So again, really try to break it down into simpler parts. When you look at this, don't try to take it as a whole unit. Say, well, one of them's in the center, one of them's at the corners, and one of them's on the faces. Corners is 1, body center is 1, faces has to be 3. Which one of the following statements about steel is false? And you should really get this. We just did this. Where? Oh, atoms. Oh, okay. Yeah. Oh, carbonatoms. That's awesome. I'm not sure what those are, but read what I meant, not what I put. It is easy. So, carbon atoms are definitely in the interstices. The presence of carbon-iron bonds now where it makes steel harder and stronger than pure iron. We talked about that. Pure iron is relatively soft and ductile because it lacks directional bonding, so it's not going to be really okay for weapons and whatnot, but still, iron weapons tend to break. The amount of carbon directly affects the properties of the steel. The more carbon, the stronger it gets, those become brittle. So you can have really strong carbon steel, but it won't shatter. So it's E, all these are true. Okay. Who feels like their brain is full for the day? All right, well, we'll call it.